All right, let's dive into an absolutely incredible story. Think of it like a 400-year-long family drama. It's all about how three of the biggest players in science, physics, chemistry, and mathematics, didn't just, grow up next to each other. They actually pushed, pulled, and shaped one another through some pretty intense rivalry, amazing discoveries, and in the end, a kind of reunion.
And this is really at the heart of the whole thing. Are we uncovering a hidden reality that was always there, just waiting for us to find it? Or are we just inventing ever more clever languages to describe what we see? Is it discovery or invention?
You see, way back before the 17th century, these fields were all kind of jumbled together under one roof. But then, this family split apart, and our three siblings, physics, chemistry, and mathematics, all went their separate ways, each one determined to forge its own identity.
Okay, so let's set the scene. It's the 17th century, the family of natural philosophy is breaking up, and it all kicks off with one of the most famous and frankly bitter rivalries in the entire history of science.
So physics, in the form of Isaac Newton, desperately needed a new language to talk about motion and change, and its estranged sibling, mathematics, delivered. The only problem? It was invented twice at the same time by Newton over in England and by Leibniz in Germany. Newton thought about it physically. He called it fluctuance, like the flow of a river. Leibniz, though, he saw it as a beautiful abstract system of symbols, and yeah, it's his notation we all use today. The fight over who got there first was so nasty, it basically split the European scientific world in two for 100 years.
So while physics and math were busy arguing over their powerful new language of equations, their other sibling, chemistry, was kind of stuck in the past. It was still living in the world of alchemy.
For an alchemist, an element wasn't something you could actually hold in your hand. No, it was this abstract idea, a philosophical principle. And you just can't build a real, testable science on concepts like that. Chemistry needed a serious reality check.
And that reality check came from this guy, Robert Boyle. In his game-changing book, The Skeptical Chemist, he came up with a totally radical new idea. He said, forget philosophy. An element is simply a substance that you cannot break down any further in the lab. That's it. This was huge. It yanked chemistry out of the world of mystical ideas and planted it firmly in the real world of experiments.
So, moving into the 18th century, the siblings are not just separate anymore, they're creating their own distinct languages. And as they grew up, these languages became more and more abstract and way more powerful.
I just love this quote. It's so bold. See, after Newton used all these drawings and geometric shapes to explain physics, Lagrange came along and said, nope, we don't need them. He wanted to turn physics into pure, beautiful algebra, a system where you could figure out the universe just by moving symbols around on a page, without ever needing a picture.
And this right here, this single elegant equation, is what he came up with. Now, don't worry about what all the symbols mean. The amazing part is that this one line of math could describe the motion of pretty much anything, a pendulum, a planet, you name it, with incredible elegance. It was like physics had become a form of mathematical poetry.
At the same time, chemistry was having its own huge breakthrough. Antoine Lavoisier, with his super careful measurements, proved that when something burns, it's not releasing some magical fire spirit called phlogiston. No, it's just combining with a real, physical substance, oxygen. His law of conservation of mass, that nothing is lost, nothing is created, gave chemistry its own rock-solid, rigorous language.
Okay, so by the time we get to the 19th century, the siblings have become so powerful in their own right that they start to realize something important. To tackle the universe's biggest, most invisible secrets, they were going to need each other again.
And this was just a monumental moment of reunion. Using a brand new dialect of math called vector calculus, a guy named James Clerk Maxwell did something that just blew everyone's minds. He showed that electricity, magnetism, and even light itself, three things that seemed totally different, were really just different aspects of one single underlying phenomenon, electromagnetism.
And this illustrates another incredible connection. Ludwig Boltzmann basically built a bridge between two different worlds. He showed that the things we can see and feel in our world, like temperature and pressure, are really just a large-scale result of the chaotic jiggling motion of countless little atoms that we can't see. His formula for entropy basically said it all, just boils down to probability.
Meanwhile, over in chemistry, Dmitry Mendeleev did something that was pure genius. He wasn't just making a list of the elements. He saw a deep, hidden pattern. His periodic table was more than a chart. It was a tool for predicting the future. By leaving gaps in it on purpose, he was basically saying, hey, there are elements we haven't found yet, and they're going to fit right here, and this is what they're going to be like. And you know what? He was right. It was proof that chemistry had its own profound, almost mathematical structure.
And then, the 20th century arrived, and it just broke everything. All the old, comfortable rules of reality were thrown out the window, and the only way this was possible was because of the shocking, almost destined partnership between physics and pure math.
So just imagine the massive problem Albert Einstein was facing. His theory of special relativity showed that space and time weren't fixed. So if gravity isn't a simple force, but is actually the bending and warping of space and time itself, what kind of language do you even use to describe that?
And here is where the story gets just wild. It turns out mathematics had already invented the language he needed. Decades earlier, mathematicians like Riemann had developed the geometry of curved spaces just as a pure thought experiment with no practical use in mind. It was a perfect solution just sitting on a shelf, waiting for a problem. For Einstein, it was a ready-made gift that perfectly described the curvature of space-time.
And this new physics didn't just explain the cosmos, it also solved chemistry's biggest mystery. Why do atoms stick together in the first place? Well, the answer came from the totally bizarre world of quantum mechanics. The chemical bond wasn't like tiny hooks or glue. It was a weird quantum effect called exchange interaction, a deep mathematical rule about how electrons have to behave. Physics had finally given chemistry its fundamental instruction manual.
And that brings us to today, to our modern era, where the three siblings, physics, chemistry, and mathematics, have finally come all the way back together, united by a powerful new common language that nobody could have possibly predicted.
Just look at this. This is the mathematical backbone of what we call the standard model of particle physics. It turns out that a super abstract field of math called group theory, which is really just the study of symmetry, happens to be the perfect language to describe the whole zoo of fundamental particles and forces in the universe.
And now, a new force has totally changed the game, blurring all the old lines. Computation has become a third pillar of science, right up there with theory and experiment. We can now simulate everything from how a complex protein folds in a chemistry lab to how an entire galaxy forms out in space, all using the same fundamental language of algorithms.
So when you lay it all out like this, across 400 years, you can really see the dance, can't you? You can trace it century by century, from calculus driving a mechanistic worldview, to abstract geometry helping unify forces, to group theory helping us rewrite reality itself. Each time, one field had a breakthrough, and it became the essential tool for the others. It's this constant rhythm of separation, innovation, and powerful reunion.
From a family fight over calculus all the way to a grand reunion powered by computers, the story of science is one of constant, collaborative creation. Which leaves us with one last, really big question to chew on. Are we discovering a reality that is fundamentally mathematical, or are we just getting better and better at inventing the languages we use to tell its story?